Hey everyone, I'm going to try to keep this video relatively brief for those of you that were taking your test today, so you were not able to join us in class. Most of the calculations you should be able to follow through on your own. I would like for you to just pause this video now, try to get through the calculations on your own, and then come back and just do the wrap up with us, okay? So, welcome back. I'm hoping you already paused and did that. The key is already on Classroom, so you can double check your work. We have a scenario when we are trying to predict someone's IQ. And we have three different counselors. The first one is the new guy. They're nervous about being wrong, so they use the average of the IQ scores after they got mixed up to try to figure out whose IQ is, which number belongs to each student. Well, they're like, you know what, I want to average all the numbers and I come up with an average score of 103 after you add all these up and you divide by 5. So they assign the same IQ for every student. Well, the next counselor comes in and says, you know what, I see an equation on the board. I am going to use this prediction equation to figure out the IQs because I know everyone's GPA. And this is, excuse the typo in the notes here, it should be 57.3 plus 16 times GPA. And when we plug in our values, our GPA into this equation, we come up with these values that the counselor number 2, came up with. You should be able to get all those values on your own. Then comes the truth seeker, this counselor. This counselor decides to pull all 5 students out of class and ask them what their IQ score is. That's given that everybody knows their IQ score, which is not really something that, it's not a test everyone takes. Not everyone knows their IQ score. All right, so we want to figure out who made the better predictions. Logically, we want to think that the more information we have about a person, the more likely we are to make a better prediction, right? So that's what we're going to go for. So we're going to check out all their errors, right? Well, the first counselor predicted an IQ of 103 just down the line, everybody having the same IQ. Well, once we found out the actual IQ scores, here they are, we subtract them. See how it says error? That's just your residual, right? We calculate the residuals and then we square that error, and that's where all those values came from in the bottom row. Once you sum those squared errors, those squared residuals, you have a value of 730. Moving on down, counselor number 2, the veteran. That's the counselor that used the line of best fit to make the predictions. Look at these values. They're far closer than they were for the counselor number 1, the new guy. Not exactly on the nose, but not too far off. Here's the residuals, the errors, actual minus predicted for this counselor. And then we go ahead and we square every value. The sum of the squared errors is 89.89. It's far lower than the sum of the squared errors of the first counselor. Remember, when we're doing the least square prediction line, that's what we're looking for. The smallest squared errors that we can possibly have while still going through X bar, Y bar, right? That should be coming together for you a little bit. So I hope you agree that the veteran counselor did better. Her sum of squared errors was 89.89, which is far less than the sum for the new guy who had a score of 730. Okay, you want to minimize that error. Here, I just copied the numbers down again so I could work with them here. Now, when we want to calculate the percentage of improvement of the sum of squared errors from the one counselor to the second one, okay, go ahead. We have the sum of one minus the sum of the other divided by the sum of the first, and we get a 0.877. Lo and behold, this is our R squared value. Here it goes. Here it goes. If you were to plug in all these values in your calculator and run a linear regression, you would get your R and R squared value that match this. Well, if you square root 0.877, please remember there might be some rounding error here, right? Because the calculator does a more precise job of this. You would still get these values, which is wonderful. Now, when we're asking you to find this S value, what we're looking for is a typical error. So they're asking us about guidance counselor number 2. So we take that person's squared error, divide by the number of people that they were trying to estimate the IQ for, and square root it, right? Now, because we want to undo that square that we had. See how this value is a little bit different? When you do it by hand, you get 4.24. Your calculator, and I'll show you how to use your calculator to do that in just a moment, gives you 5.473. This brings us back to our degrees of freedom. And I know we have not really dived into this too deeply just yet. It's going to keep coming up. It's going to make more sense when we get closer to semester 2. But remember, our guidance counselor number 2 used a prediction equation, so that's an estimation, to make another estimation, right? So we're estimating his or her typical error from an estimated IQ. That's 2 degrees of freedom removing away from the actual data, right? So we estimated once, we're estimated again, 2 degrees of freedom gone. So in order to get this value, we shouldn't be dividing by n. We're losing 2 degrees of freedom. We should be dividing by n minus 2, which in this case is 3. If you go ahead and you try 89.89 divided by 3, then square root it, you will get much closer to the 5.73. You will never be asked, once again, to calculate those values by hand. Honestly, it's beyond the scope of this class, but I do think there's value to seeing where these numbers come from. Some of you have a better grasp with the material than numbers right away. Some of you perhaps might struggle to make sense of where those numbers are coming from and what they mean. So I'm hoping this activity helps you see where we're getting these numbers from, okay? So before we go into the calculator portion, actually, let's go to the calculator right now. Let me pull my calculator up real quick. All right, I did take a moment to plug in my values already to save time. Whoop, here we go. So we have these values. Usonce you get everything plugged in, please remember to go ahead and run your regression. We are using our GPA to predict IQ. Okay, so we've got our R and our R squared value. Here they are, very close to what we calculated by hand. Don't forget that now you want to check first. Oh, I'm sorry, wrong thing here. I'm sorry, escape out of here. I want to check my scatter plot first using GPA to predict IQ. Well, I like the scatter plot. I have a strong R. To me, this looks fairly linear. But before I make a decision, I'm going to check my residual plot, which means I'm going to go to the y-axis here and change this into stat.resid. And I see here that I have, oh, let me move the cursor out of the way. It's only a few data points, right? But it still looks fairly scattered. I don't see a U. I don't see a V. I like this. I can go with this, all right? So now let me go back to right here. We have our R, we have our R squared, we can get our prediction equation, and we're talking about finding that S value, that trying to remember the value, 5.73 that we came up with a minute ago. You'll never be asked to calculate this, but if you're interested and you want to know how to calculate it, once you're in this window, click Menu, choose Statistics, and choose Stat Tests. Okay, we're going to do a lot more of this next semester. We're never really going to run a linear regression t-test. We're going to do all kinds of other t-tests, but for this specifically, if you want to get the S value on your own, you click here, again, choose the same variables using GPA to predict IQ, and you do not have to change anything else. Click OK, and let me scroll down to find it. Should be a little bit further down. Here's that S value of 5.73. You don't have to write down every digit. You're fine with rounding to the nearest thousandth. So let's go back to those notes. Make sure we figure out how we're going to name all these values, how we're going to interpret these values. That's the most important part in our class. Context, context, context. Super important, okay? We know how to translate R into statistics talk. We've done that many times now. Now for R squared, everything that's in blue can stay as is for any problem at all that you're dealing with about whatever your percentage is, about R squared percent of the variability in your IQ can be explained by an approximate linear relationship between IQ and GPA. You could also say about 87.7% of the variability in IQ can be explained by our linear model. That's it. Good enough. You have your context, you have the percentage right there, you are saying that it's discussing variability, you are done. Now, as far as S is concerned, our standard error right there, what you want to say is that if our least square regression line or linear model is used to predict IQ from GPA, a typical difference between predicted IQ and actual IQ would be about 5.73. And I'm going to add in another short, this is very precise. Here you're not losing any points, but it can be tricky to remember how to phrase this. So I'm going to add in a simpler, still correct way to explain this. The actual Y context, whatever your problem tells you to do, is typically about your S value away from the predicted value by the least square regression line. So here we would say the actual IQ score is typically about 5.473 points away from the predicted value given by our least square regression line. Done. For most people, this is easier to remember, but I feel it's my responsibility to give you the full answer right there. Okay. Now there was another activity we were discussing in class about influential points and our outliers. So I'm just going to give you the download on this one. Influential points. If they influence the line and our R value drastically, that is an influential point. So see how here we have, pretend this red dot is not there for a second, right? This red dot is not there. Our linear model, we have the line going right through here, right? Okay, it's going right through there where the blue line is. Now when I add in this red dot, see how far off it is in the X direction horizontally? It's far off from everyone else. Well, it's going to pull the line in its direction. Don't forget, our line has to go through X bar, Y bar. This point adds a very large X value, which will pull the mean in its direction. So it's going to change the position of our X bar, Y bar. This point will change. Look at this red line. Look at this red line, how far off it is. It's changing the slope. It is changing the R value. It could likely change the Y-intercept. It's just throwing everything off. It is a very influential point. It influences our decision. Let me show you a different example. Ta-da! All right, pretend this point right there, this one, let me just put a dot over it. This guy's not here for a second, okay? Pretend this is not in our chart. I have a beautiful linear model. The data points are just so close, compact on my line. It looks phenomenal. Now I'm going to go ahead and add this point in. Think about your X bar, Y bar. Well, the X value of this point is still within all my other X's. So my X bar will not be heavily affected. I hope you agree. Now the Y value of this point, it's still within the range of my Y values. So I shouldn't expect a drastic difference to my Y bar. It's not really going to affect my X bar, Y bar value tremendously. All right. This one, it's going to have, it doesn't fit the trend, so it will have a large residual, but it's not going to throw my line completely off, right? It's not going to destroy everything. This is an outlier. I know we have always talked about the outlier pulling the mean in its direction. It will have a slight pull, but it's not going to have this tremendous impact because the X value and the Y value are still within the range of the X and Y data points that we have. It's not drastically different. High leverage points, this almost never comes up, but why not talk about it? See how here all these guys are grouped together? And then we have this point right there. Well, the line is not really changing its direction, but now once you add this one right there, this point that is really far off in X and Y direction, it's going to make you feel like it's going to give you, not make you feel, it's going to give you a stronger R value. When really, if you look at the rest of the data points, we don't have such a strong association. We shouldn't have a very large correlation coefficient. Over here, this one is high leverage. It's not going to have a very large residual, if any, because the line would fit right through it. Same with this guy. The residual, we're not expecting a large residual right there. It's going to be very tiny. But it is high leverage because it's going to give you a stronger R value because it's going to make the line longer. It's going to make you think that you can predict that everything within this range, it's still interpolation. When really, this guy is far off, right? So everything in here could still be extrapolation, right? Because we don't have any data in between. This guy just came out of left field. It changed everything. Let me erase my handiwork here so it doesn't look so messy. All right. This guy will have a large residual, once again, the outlier. It's not very high leverage because it's not throwing everything off tremendously. We can still have a pretty good prediction line. So it's not heavily influential. Right here, this guy, if you can see the red dot, if I have my line here, it would be right there. Now this guy is really, really off in the y direction. So my line is going to try to tilt down. It's not letting me tilt it the way I want to tilt it. Anyway, so it's going to start, let me change the color so it makes a little bit more sense. It's going to try to include that point, so my line might end up looking kind of like this. And it might even move further down. I mean, I would have to plug in the points to see exactly where it would go, but my line is going to change, right? So this one is influential because it's going to change my R value, it's going to change my slope, it's going to mess with my data. All right, quick check. A point that stands away from the rest. Again, this is something that's unusual. You do have to mention it when you're describing your R. You're talking about it is linear, for example. It is strong. It has whatever R value you have to mention everything: direction, strength, and form. Linear, nonlinear, strong, and so on. So this is an unusual characteristic. You want to talk about it. Okay, if we see an influential point or we see an outlier. If it has an extreme X value, extreme low or extreme high, it's typically influential. If it has a rather typical X value, but its Y value is more extreme than you would expect, then you call it an outlier. Okay? No one's going to come after you if you get one of these wrong. If you call it an unusual characteristic or you feel like it's an outlier, no one's coming after you for not calling it influential and calling it an outlier. But it's good to explain the difference between the two. So with that, I am going to say goodbye to you. Please check in with me if you have any questions. And homework is another video about transformations. Thank you so much. Have a wonderful day.